Hi, this is James talking about risk analysis using Bayesian networks. A Bayesian network is a model that can be built from expert opinion. It's to assist with decision making and reasoning and is based on probability thinking. If you'd like an introduction to Bayesian networks, there is a link at the end of this recording. The linked video demonstrates the use of Bayesian networks in two simple cases. The first is known as the Harvard Medical School problem, which models being tested for a disease. The other models a fictitious chest clinic, which presents a simple patient diagnosis based upon symptoms and patient information. As you can see, the Bayesian network presents a graphical representation of the models. Now let's look at risk. This matrix shows risk as the result of two factors: consequences, what impact would the risk have if it occurred, and likelihood, how likely is the risk to happen. So the higher the likelihood and the more severe the consequences, the greater the risk. We can model this risk analysis tool using a Bayesian network. Here we have a 3-node network. Consequence, with inputs ranging from insignificant to severe. Likelihood, with inputs ranging from rare to almost certain. And the resulting risk is the output, ranging from very low to extreme. These values correspond to the inputs and outputs in the risk matrix. Now we show this network modelled using Netica, a software package for building and running Bayesian networks. Here we have the Netica application with the risk model loaded. The network is in the no evidence state, which is usually a statistical average. In other words, moderate is the most common likelihood and insignificant the most common consequence. The first column in the matrix represents the possible risk values for insignificant consequences. Using the model to represent that, I select insignificant in the network's consequence node. The risk node immediately shows that possible options are now very low through medium. Next, we will step through the likelihood cases and show how the Bayesian network matches the matrix, from rare to almost certain, resulting in risks from very low to medium, consistent with the matrix. So we now select an input of rare in the likelihood node. This results in a risk of very low, consistent with the risk matrix. We then select unlikely, and the risk is the same, also consistent with the risk matrix. Now select moderate, and the risk is low. Now select likely, and the risk is medium. Select almost certain, and the risk is also medium. Now let's move diagonally through the risk matrix from low risk to extreme risk. Low is unlikely and minor. Selecting those options in the Bayesian network, we have unlikely and minor, also corresponding to a low risk. Similarly for medium risk with inputs of moderate and significant. Very high risk with inputs of likely and major, both in the Bayesian network and in the risk matrix. And extreme risk with inputs of almost certain and severe, both in the Bayesian network and in the risk matrix. So we can do forward reasoning from cause to effect, from likelihood and consequences to risk. But one of the cool things about Bayesian networks is you can also do backwards reasoning from risk to likelihood and consequences. First, we reset the network back to the no evidence state, like so. Let's say you don't want any extreme risks. These probability bars also act as sliders. I can click on the bar representing extreme risk and slide it to the left to reduce it to 0. The rest of the model adjusts to show what ranges of likelihood and consequence lead to that risk profile. Now let's reduce the very high risk bar to 0 as well. This shows the distribution of inputs. Now setting high to 0 has this distribution. Now setting medium to 0 shows that for below medium risk you must have moderate or below likelihood and mainly minor or below consequences. As you can see, we can select the desired outcome and see what the necessary inputs would be to achieve that outcome. This will become particularly useful in more complicated cases. So how did all that work? Behind the risk node is a table called a function table, which defines all the outputs based on the various inputs. Here we have the function table showing the risk value for all the combinations of likelihood and consequence. You can see that the function table corresponds to the risk matrix. For example, if we pick out the moderate likelihood and significant consequence, you can see that both the table and the matrix give a risk of medium. Okay, so a 3-node network isn't that exciting. We could have used the risk matrix instead. But the Bayesian model can be extended, of course, to more advanced use cases very easily. Next, we want to model the risk associated with installing and running an IT system or network. In other words, the cybersecurity risks. Looking at our simple model, for the consequences node, it is relatively easy to determine what values apply if we understand what data the system or network is handling. If it's a banking application or network, for example, the consequences of a data leak or compromise could be severe. It's the likelihood node that is the harder element to model. How are we going to do that? It turns out a lot of good work has been done in this area. An article on cyber risk assessment using Bayesian networks has been published by Ramakrishnan. His article shows the design of a Bayesian network to calculate the likelihood of a data leak for an IT system or network. So let's look at Ramakrishnan's likelihood model. Here is a simplified version of that model. The green nodes show overall system controls and vulnerability controls. These influence the outcome, which is the likelihood of a data leak. The initial values entered are for demonstration purposes and show an average state having controls that are not effective. So we have the intermediate nodes in green with the yellow nodes upstream. For example, the malware control node contributes to the vulnerability node. The network is in the no evidence state. We know nothing about a new system that has been submitted for assessment. For demonstration purposes, the network is saying, on average, our controls are mostly not effective, 40%, with 30% being slightly effective, and only 5% being extremely effective. In turn, this means our overall system controls are 91% not effective. Vulnerability controls are 78% not effective, and the data leakage likelihood is 91% almost certain. Note again that the values are not Ramakrishnan's but are for demonstration. Let's say the system we are assessing has effective malware control. Let's do that now. Using the Netica application, select moderately effective on the malware control node. We will notice an improvement in the vulnerability controls, the overall system controls, and a slight improvement in the data leak likelihood, like so. Vulnerability controls have decreased from about 80% not effective to 64%. Overall system controls have decreased from 90% to 86%, and data leakage likelihood has reduced from 90% almost certain to 86%. Now let's say we find out that patch management is also moderately effective. We select moderately effective, and the vulnerability controls improve further. And if application controls are moderately effective, then vulnerability controls as a whole are also moderately effective. But this hasn't changed the overall system controls that much and hasn't reduced the data leakage likelihood significantly. Why is this? Well, without detailed input from cybersecurity experts, This demonstration model uses a simple weakest link type approach where it assumes the worst case. If any control is not effective, this will have a big impact. For demonstration purposes, this will suffice. We now learn that local admin control is moderately effective, and we start to see a significant improvement in overall system controls, and data leakage likelihood ranges fairly evenly from moderate to almost certain. Finally, we find out that external storage control is effective, and the overall system controls reflect that, and data leakage likelihood is reduced to moderate. Now we want to show how easily the model can be extended. We add in some physical controls and network controls, which in this simple model we have chosen to represent like so. On average, our physical controls are very effective, and our networks are mostly isolated. This has reduced the data leakage likelihood to mostly unlikely. If we now find out that the physical security for a particular network is moderately effective, we see a significant improvement in physical controls, and data leakage reduces to 90% unlikely. Finally, we learn that it's an isolated network. Physical controls are very effective, and data leakage is unlikely. We now want to plug this into the original risk model combining likelihood and consequence with a resulting risk. Like so. As before, data leakage is unlikely, but we have no knowledge of the consequence. This is in the no evidence state and is based on our previous experience. In this model, our most common experience is with systems with insignificant consequences. However, there are some with higher consequences, and as a result, the risk rating ranges from very low to high. Let's enter a consequence value for a particular system or network. Let's say it has insignificant consequences. This gives a very low risk rating, whilst if we are dealing with severe consequences, it results in a high risk rating. So once again, we've shown forward reasoning from cause to effect. But recall we can also do backward reasoning. We can decide what outcome we want and see what the required range of inputs are. So we start off by resetting the network back to the no evidence state. This might represent the average state of all your systems and networks. Let's say you'd like to reduce your risk ratings, and you'd like to start by reducing the likelihood of a data leakage. Recall that these probability bars act like sliders, and we can click on them and adjust their value. Let's reduce the almost certain cases to 0 and the likely to 0 as well. The model adjusts to show the required inputs to achieve this outcome. We see that the model suggests that extremely effective physical/network controls would lead to that outcome, as well as some improvements to system and vulnerability controls, but to a lesser extent. So we have seen we can use a Bayesian network to model the risk of installing and running an IT system or network. It starts off in the no evidence state, and we can add evidence as we discover it. And we can improve the model easily by adding to it. And importantly, not only can we reason forwards from cause to effect, but we can do backwards reasoning from effect to cause. So we can decide what risk is acceptable and work backwards to see what the model predicts are the required inputs. So thank you for watching. I just want to highlight a couple of references and the link to an earlier video. These are the references: Ramakrishnan's model of data leakage likelihood, a book by Fenton and Neal on risk assessment and decision analysis with Bayesian networks, and the Netica software. And here's a link to an earlier video if you haven't seen it. Thanks again for watching.